Okay, so today we have Craig H. Williams from the NASA Glenn Research Center with us, and he's going to present an overview of NASA's recent planning for sending humans to the planet Mars. And I am very excited to learn about this. So thank you, Craig, for joining us, and I'll go ahead and turn it over to you.
Okay, thanks, Amy. And good evening, everyone. I have a presentation here that has a lot more charts than we have time to get through, so I'll be skipping through them and not briefing every single one. I understand we have some very qualified astronomers and people interested in outer space, so I'm going to save the tutorial charts for another time and use some of this opportunity to ask you tough questions, not just get tough questions asked of me. It is a presentation about humans to Mars, but I am required to give you a disclaimer that while the material I'm basing all this on is NASA material, it does not represent an official currently being formulated mission baseline for ongoing planning. It's just informational only. There is no actual funding for a manned-Mars mission at this time, just preliminary studies that have down through the years been done. And as we know, physics doesn't change. The difficulty of getting from the Earth to Mars remains the same. So when we finally do get turned on, the material that I'm going to be describing to you that NASA has performed and done will still be relevant. Again, there's a lot of material here, but I'm going to be focusing on the three key problems, primarily the first of the three key problems of getting people not just to Mars, but to any of the planets. The first problem is, of course, the need for advanced space propulsion technology. That's where most of my background is. There's also two very important problems that come with a manned Mars mission, and that is the need for artificial gravity and the need for protection from ambient radiation that naturally occurs in outer space. These are the three key areas. Almost everything else about sending people to the planets is solvable, okay? These are the three that really are the tall poles that stand in the way of why we have not been able to send people to the planets all this time since the moon landings. I do want to start with a few. By the way, I will get you out in no more than an hour, I promise. I'll be finishing up in about 45 minutes, at most 50 minutes, to allow at least 10, maybe 15 minutes for questions and answers. For those of you who have not been to the NASA Glenn Research Center here in Cleveland, Ohio, I strongly recommend it. After 9/11, like all federal facilities, we have more stringent access requirements, but we still are taking groups of people on tours. It just has to be coordinated well in advance. The main campus is about 350 acres in size. We have over 3,000 people, half civil servants, half contractors, staffing 150 buildings here on campus. We also have a remote facility, Plumbrook Station, out in Sandusky, which has some of the largest testing centers for rocket propulsion and space power in the world. So it's really a phenomenal national resource here, and I strongly encourage you to come and visit us. We just celebrated our 80th anniversary since our founding. There are a variety of space propulsion technologies we've done through the decades: chemical rockets, electric rockets, nuclear thermal, which is splitting of atoms, and even nuclear fusion type rockets that we've studied and done some preliminary experiments on down through the ages. But we're going to be concentrating on nuclear thermal for the Mars missions. Our heritage in launch vehicles is one of the main reasons why we remain involved with the Mars mission planning. For 35 years, our center was in charge of launching unmanned rockets to Earth orbit, to the moon, and to the planets. And it's our experience in that is invaluable in using that for planning for the Mars missions. I had the luxury of spending the first 10, 12 years of my career doing trajectory design for launch vehicles, including a couple that you see here in this picture, the Titan IV Centaur mission, Cassini mission to Saturn, and the Atlas Centaur CREST mission to Earth orbit on Atlas Centaur. But for 35 years, the Lewis Research Center, now the Glenn Research Center, has launched 119 missions, also, obviously from our pads, primarily from the East Coast, some from the West Coast, but the mission planning, the integration, the launch vehicle development work was done here in Cleveland, as well as with our contractor partners. As far as people always ask, well, are there plans? Are there official plans? Well, for over the decades, there have been studies, and depending on which president and what administration, it keeps vacillating between Moon, Mars, and low Earth orbit. It's not a political, it's not a partisan thing. Each president, along with their administrations, have different ideas on what we should be concentrating on. And of course, NASA, like the rest of the government, we work for the elected representatives of the people. So for example, the first George Bush, he focused on Mars. So that's what we focused our planning on. And then President Clinton wanted to emphasize low Earth orbit, primarily building and operating the space station. When the next George Bush came in, he wanted a balance between Moon and Mars, and he redirected it towards the Constellation program. When President Obama came in, he wanted to focus exclusively on Mars, and as far as launch vehicle development, the Space Launch System. When Donald Trump came in, he wanted to focus on the Moon with an eye towards Mars, but primarily, a lunar type of mission. Now, the current president, President Biden, he has not issued policy. Well, I'm getting ahead of myself right now. So ever since, actually, as far back as the early 1960s with the Empire studies of manned-Mars flyby missions, depending on which administration we're talking about, they had different ideas. So it's always changing. Although the policy changes, though, the physics of sending people on interplanetary travel does not. The distance and the energies between the planets does not change, obviously, for time. So although there's been no funding for Mars missions, manned Mars missions, most, if not all, of the studies and the early experimental work, it remains relevant. No matter when we decide to go to Mars, it will still be relevant work. We still will need a heavy launch vehicle to get supplies and people on their way. The interplanetary crews and mission operations remain the same. The policy from the former president, President Bush, remains in place. That's not surprising. No matter which administration, there's always a lag between the election and change in policy for NASA. We're not on the first tier. The big federal agencies, the State Department, the Defense Department, the Treasury Department, they, and rightfully so, get the first attention of the new president. NASA, we're the second tier. And so we don't see a change in policy until 6 to 12 months into administration. So we're sort of on autopilot. That's fine. That's what always happens. And we expect a change in formalizing of President Biden's direction for NASA, in the months to come. So we remain focused on the moon planning, and it probably will be largely the same, maybe different emphasis when President Biden can focus on where he wants NASA to be. But the eye is on Mars, but initial planning is to test out a lot of the same technologies on the moon. Okay, that doesn't mean that the robotic mission is on autopilot. I assume most, if not all of you, are familiar with the characteristic differences between Mars and the Earth. I won't belabor that. As far as the current unmanned probes, we've had a lot of success with the rovers. Perseverance, of course, is the most recent one with the Ingenuity helicopter. I'm sure you've been reading and up on the successful launches and flights of the first helicopter on another planet. And Mars Science Laboratory, which was also a rover the same size and capability of Perseverance, those have been success stories. More about InSight Lander in just a moment. Perseverance, along with this helicopter, landed some time ago. This is a large vehicle. It's designed to search for signs of ancient microbial life, drilling core samples, and looking for and sealing those samples. Eventually, they will be returned to the Earth. So this is something new. This is something really exciting. we don't have the capability of returning anything to the Earth at this point, but that's that will be the focus of upcoming launches of upcoming spacecraft in the near-term years to come, to take the samples that Perseverance has encapsulated and return them for the Earth for study, and test technologies for future human exploration of Mars. And of course, the helicopter was more of a proof of concept that you actually can have controlled flight on another planet. So that's been an exciting success already. This is one of the more recent photographs from the Perseverance rover of the surface of Mars, where it is located and where it's starting out its exploration. Now, the Mars InSight lander, unfortunately, has been a different story. Let's start off with a positive. The seismometer has been a success. That's that domed instrument you see in the upper right-hand corner. That's an actual photograph from InSight, and the illustration of it, the artist's view on the lower left. That is designed to measure Mars quakes and the internal structures of Mars. That has succeeded. The heat flow probe has been a different story, unfortunately. That has basically been shut down. It's failed. It was supposed to drill down approximately 16 feet. It got down to a little bit more than a foot. Unfortunately, after a year of trying, that has not performed as we had hoped. Sometimes things succeed, sometimes they don't, and unfortunately, we have to learn from our mistakes on that one. That is just a lander. That's not a rover. And of course, MSL, the first major rover, that continues with its mission to search for signs of life, and also the geology. The geologists have told us that these type of structure that you see, especially the upper picture here from MSL, is the type of structure you'd see when you have some type of liquid flowing over the surface of a body, sedimentary type rocks. You don't get that without some type of aqueous solution. So this is, indirect evidence that we're seeing that we actually had some type of fluid, be it liquid water or something else, flowing on the surface of Mars sometime in the distant past. A couple of the other orbiters remain in operation. The MRO being one of them. Odyssey is when we saw some of the geology that we see reminiscent of, again, aqueous solutions on the surface of another planet. And this is striking. This shows you how the rovers have grown in size. Perseverance and MSL on the right, these are the size of cars, and they require a radioisotope thermoelectric generator in order to power themselves. The Mars exploration rovers, both of them, are the size of human beings. You see the two researchers there. And the little rover, Sojourner rover from the late 1990s, that's almost like a toy by comparison. So there's been dramatic increase in size and capability of the rovers over the last 25 years. And of course, Mars Global Surveyor is one of the things that has kicked this whole thing off in the early 1990s, where in the polar regions, the North Pole in particular, we see beneath the surface, of course, we have ice caps with their dry ice, carbon dioxide, as you all know. But actual water ice below the poles is what got us interested and excited about. There was likely flowing water on the surface of Mars in this distant past. This is why we're excited. The whole idea of following the water to try to find evidence of life in the past, and something that could be used as a resource for both human being consumption as well as propulsion in the future, if we can actually make use of in situ resources like water in the poles of Mars. Other evidence, indirect evidence of flowing surface water, so-called hematite blueberries at the Opportunity site. Again, the geologist tells us that you can't get geology like this unless you've had erosion with flowing water on a surface. And that's what we saw from the Pathfinder on an otherwise very dry surface. So why send people to Mars if we can do all these things with robots? Well, there's several reasons. There's many reasons why mankind explores unknown worlds. For Mars, of course, it's primarily scientific interest, extraterrestrial worlds, to try to find evidence of life off the Earth. If we can find that, I mean, that would change our whole perspective on how life started here on the Earth compared to another planet, and eventually how human beings evolved from lower forms. So that's the primary focus on that. Of course, there are other things, you know, survival of the species. Can you eventually send people to Mars and to expand human, you know, life, you know, in other planets, not just here on the Earth? Frequently, you hear the comment, you know, human versus robotic. It's really, I would argue, a false choice. They're complementary to each other. The right question is how much of either. You know, robotic, you can do an awful lot with robotic missions. They are much less complex. They are much less expensive. They are much lower risk. However, they can't do things that people can do, right? You know, they can change the experiment to capitalize on unexpected discoveries. It's hard to do that with a robot. You can, you know, software is malleable, but there's just a limit to how much you can do with a robot that has experiments already designed into it. Human beings, if you put a human being in a laboratory on the surface of another planet, he can leverage discoveries. He can extend the discoveries that robots find and change the experiments. There's an enhancement of international prestige by sending people to another planet. Can foster international cooperation when you bring in the other countries, and certainly leveraging cost is another big thing here, and others. You know, a good example of the limitations of robotic landers is what we were just talking about moments ago, the InSight lander heat probe. Now, this is dated information. I should have updated this, but you know, we've been trying for well over a year to get that heat probe, that drill, to work, and we never were able to really do it. You know, we tried all sorts of things to push that probe down with their robotic arm. We've tried all sorts of things. It only got in about a foot instead of 15 to 16 feet. So it's very limited in what you can do when you get into trouble with just a probe. But if you have human beings on the surface, we've got our ingenuity. We're infinitely more capable than a robot. We could have altered that and made that experiment succeed, whereas a robot could not. What other impacts? I got this from another questions from another presentation. What other impacts from a manned Mars mission would we have here on the Earth? How would you actually, by solving problems of sending people to Mars, apply it to Earth? Sometimes in applications have nothing to do with exploring the planets. You know, developing a high specific impulse propulsion system for fast human missions like nuclear thermal propulsion can increase payloads such as communication satellites here on the Earth for Earth missions. Peaceful use of highly enriched uranium. You know, how do you get rid of uranium from especially sources where you want to make sure it doesn't end up as weapons? Well, nuclear thermal rocket is a good application for that. How to deal with ambient radiation that you no doubt will have when you send people to another planet. Improve radiation protection, cancer treatments, airline pilots who are subjected to increased dosages because of the nature of their work. We have to learn how to deal with zero gravity countermeasures. Understand that can lead to a better understanding of human physiology, the role that gravity plays on that. Working with other nations, improve international relations and prestige, and others. You get the idea. There are many ways that we can apply what we have to learn from manned Mars missions on things here on the Earth that have nothing to do with space. Let me just skip over this. Let me just pull out one or two things here. How do you compare a Mars mission with Moon? Using chemical propulsion, the best chemical propulsion that's practical, locks hydrogen. It takes us 3 days nominally to get to the Moon. That's what Apollo took. To get to Mars, it would take us 6 to 9 months, not days, not weeks, but months. Whereas if we use advanced propulsion, we could cut that at least in half, if not better. Abort missions are even more critical. If we have an Apollo 13 on the Moon, it took us 6 days. We had to do a slingshot maneuver around the Moon and back. It took us 6 days to get back to the Earth, and that's with a 6 spacecraft. If you rely on chemical propulsion for Mars, you could be out in space for as long as 3 years, not days, weeks, or months, years. You don't want to do that. You want something with more capability. Again, that cries out for advanced space propulsion. And there are other issues, primarily, as we said, you know, exposure to ambient radiation and the zero gravity effects, which were manageable or minimal for the Moon mission, That will not be true on a Mars mission. You have to face that and solve it. Let me skip over that. We'll catch that in a little while. Let's skip over this. Let's skip over this. Okay, this chart is important. Why advanced propulsion, specifically nuclear thermal rockets for inner solar system missions, primarily Mars missions? I'm getting this from Dr. Stan Borowski, who is recently retired, spent the last quarter of a century here at the Glenn Research Center in Cleveland, Ohio. He was NASA's expert in nuclear thermal rocket, bar none. And if the chart, I admit it's a little bit of an eye chart here, I apologize, in the lower left-hand corner, what that shows is on the x-axis, total mission duration, that's in hundreds of days, 300, 400, 500 days along the x-axis, and total mission mass in low Earth orbit, that's 500, 1,000, 1,500, that's in terms of metric tons. You want to be in the lower left-hand corner of that chart. You want short mission duration and the smallest, lightest amount of mass in low Earth orbit. That reduces the amount of launches, it reduces the amount of cost. That's what you want. And what that chart is saying to you is the darker blue, those are the nuclear missions, and the upper right-hand corner, you can just see the word chemical. Those are chemical missions, propulsion missions. So nuclear thermal rocket dramatically reduces the amount of mission duration and the amount of mass you have to launch for the mission. That's why you have to have nuclear thermal propulsion to send people to Mars, and cannot do it the way we did it for the moon or the space shuttle or anything that we've been doing for 60 years. Unlike any of those missions, you're going to have to do like the German rocket scientist Wernher von Braun and his team concluded, 50, 60, 70 years ago, you have to have nuclear thermal rockets. It also simplifies the number of different stages that you have. And that's that table on the right that you probably can't read. I'm not going to dwell on the human factors. I'm just going to say, just touch upon it because it's not my area, but these problems are at least as important, if not more so. We've long known that zero gravity has a detrimental effect on the human body. We lose bone mass, muscles atrophy. You can do exercises to try to mitigate that. You can take certain nutrients to help stem that, but we really don't have a good solution to that. The only thing we have now is to shorten the trip time, and that's what you get when you go with nuclear thermal rockets. But it still is going to be a problem. You have to be able to make sure that after you're spending all this time and effort and money, that astronauts, when they land on Mars, can get up and start doing their job. And if they can't, then why go? We're going to have to deal with some type of artificial gravity spacecraft, which we've never had to do before. There's certain ways of doing this, but it means it's going to be a much more complicated, much more expensive vehicle in order to do that. Now, you may not need a full 1G of Earth gravity, but that's one of the main problems. We don't know how many Gs we need. Is it a half a G? Is it a tenth of a G? Is it 90% G? We don't know. And that's part of the problem, why I say this is more of a science problem than an engineering problem. The scientists have to tell the engineers how much of an Earth gravity field do we need in order to keep the astronauts healthy so that they can get to Mars and be able to function once they get there. This is a significant problem. For those of you who have seen the old movie 2001: A Space Odyssey, there's a reason why they had centrifuges all over in that movie. They talked to NASA and they said, you're going to have it one way or the other, some type of centrifuge. There they had partial centrifuges or entire centrifuges. Stan Borowski, with his concept, has the whole vehicle spinning up. It's simple enough, it's symmetric enough that you can do a concept like this and supply a partial G to at least maintain the health of the astronauts. We're not sure if this is enough, but it is a way of solving the problem. As far as ambient radiation goes, this is another problem. It comes in at least two flavors: solar flares and cosmic rays. Solar flares come from our sun. They are truly lethal, but they are directional. So it's possible to, you know, that you may escape it, but it's more likely that you are going to take at least one hit, which means that you're going to have some type of storm shelter, which is very heavy and very, well, it's not the way you'd like to design a spacecraft. You try to design a lightweight spacecraft, not a heavy spacecraft, but at least we have a solution. It's not a good one, but it will work. You know, if you jacket a storm cell with a lot of water. The other one are secondary cosmic rays. They come from all directions. They come from the centers of other galaxies all around us. That one you just need a lot of shielding for. Again, it's not a good solution, but it will work. If you don't do this, chances are you will have radiation damage to the astronauts, possibly severe. In the case of solar flares, probably lethal. They will probably take at least one flare in a 2-year round trip. So these are two serious problems that have to be solved in addition to the propulsion problem. I'm going to skip over a lot of this other things here and jump to the nuclear thermal rocket. A lot of people forget that they remember the John F. Kennedy speech about, you know, I believe this nation should commit itself to achieving the goal before the decade is out of landing a man on the moon and returning him safe to the earth. That was only one of 4 things that President Kennedy laid out. Number 3 was weather satellites, and number 4 was communication satellites, I believe. But the second one was he called for funding to accelerate the development of the rover nuclear rocket. And that was aimed at the Mars mission. We did not know if we were going to win the space race with the Russians to the moon, but we wanted to hedge our bets, and we started funding research and development for nuclear rockets to go to Mars. And that was the second point of Kennedy's speech. So this dates all the way back to the early 1960s. Stan Borowski, like I said, was probably the most prolific expert and designer of nuclear thermal rockets NASA has ever had. This is just a short resume of what he has accomplished. And it's driven by, this is a similar chart to which I just showed you, where you have total round trip missions on the x-axis and total mass, initial mass of low Earth orbit, IM LEO, where nuclear thermal propulsion, NTP, that's that blue region, and to a lesser extent, nuclear electric propulsion, they are the propulsion concepts of choice, not chemical, of sending people to Mars. A nuclear thermal rocket operates very similarly to a chemical rocket. Okay, a chemical rocket, you burn oxidizer and fuel to generate very high pressure, very high temperature exhaust products, which is expanded thermodynamically through in a convergent divergent nozzle. So you're trading high temperature, high pressure for directed thrust. Okay, what comes out of the engine is low temperature, low pressure, but very high velocity. That's what happens with a chemical rocket, but it's a chemical reaction. With a nuclear thermal rocket, what you're doing is you're creating high temperature, high pressure, but all you have is a propellant. There's no oxidizer. What you're doing is you're getting the high temperatures and pressures by passing the propellant of choice, hydrogen, through a nuclear reactor. That's what's heating the propellant. And then it's expanding it thermodynamically through a convergent divergent nozzle. You can get twice the specific impulse out of a nuclear rocket than you can with the best LOX hydrogen rocket. Specific impulse is the ratio of thrust to propellant weight flow rate. It's our miles per gallon, if you will. It's the ratio of thrust per weight flow rate. More is generally better. And with people on board, you want as much thrust at lowest propellant weight flow rate as you can get. Robots don't care how long it takes them to get to another planet. People do. So that's why you need to have nuclear thermal propulsion. And this is just another example of it. I'm going to skip over this. Here's one of Stan's many concepts where you have those yellow propellant tanks are the hydrogen. Off in the upper left-hand corner are the nuclear thermal rocket engines. They're small by comparison, and a two-floor stage transhab, inflatable transhab for the astronauts. That entire vehicle is spun up to generate artificial gravity for the astronauts. The engines are bimodal, which means that when they're not propelling the spacecraft, they can go at a lower power level to generate electric power to keep the propellants cold, to generate electricity for onboard systems, for payload maintenance, for attitude control of ion thrusters, all sorts of things. I'm going to skip over this. This is some related research. More recent concepts by Stan that could also include solar power if necessary, and also escape capsules, including the crew capsule vehicle that you see embedded in the upper illustration. Regardless of what type of propulsion system you rely on, unlike the moon missions, which were, you could do the whole vehicle, you could do the whole mission on a single vehicle. With the Saturn V rocket, you could do the whole thing with one launch. You can't do that with interplanetary missions. There's too many people, there's too many supplies, the missions are too long, and what you have to invoke is what we call a split sprint mission, where you pre-deploy a lot of assets in advance, including your return stage and some of the propellant, maybe even in situ resource utilization propellant factories. And only when they are at Mars and they signal that everything's working, you send the crew on a fast one-way mission. These people would be able to sprint, from Earth to Mars because they're not carrying all that extra weight with them. It's called a split sprint mission. And this has been studied as far back as Space Exploration Initiative in the 1988 to 92 timeframe, and remains one of the main concepts even to this day. If we were to do a Mars mission, get turned on to a Mars mission, most likely we'd do something like this that we studied as far back as, like I said, 1988 to 92, a split sprint mission. It will not be a replay of the Apollo type mission where we build one gigantic rocket and try to do it all at once. It's just too complex. The planet is too far away. It requires too much energy. The mission just cannot accommodate it. Now, a couple of new pieces of information here. This is a couple of months old, and some of you may have actually seen this. NASA and Department of Energy are now funding 3 nuclear thermal space propulsion concepts. These are just conceptual studies. This one is only a couple of weeks old, where it was awarded through Department of Energy, Idaho National Laboratory, INEL, which is the chief site for nuclear energy research. Each contract is worth up to $5 million. They're 12-month studies culminating in a reactor design concept. This is an exciting thing because this is the first new thing under the sun since some of the turn of the century type of studies. In addition to that, a month before that, the Defense Advanced Research Project Agency, DARPA, started a study of their own called DRACO, Demonstration Rocket for Agile Cislunar Operations, to demonstrate nuclear thermal propulsion systems on orbit. And there's 2 tracks on them. One of them is a baseline design NTP reactor culminating in a baseline design review, and another one to develop operational system concept. So these are, and they awarded it to 3 different companies, General Atomics, Blue Origin, and Lockheed Martin. And although they didn't disclose the amount, Space News reported, I'm just reporting what Space News reported. It's not coming from NASA, it's just what I saw in the newspapers. They're quoting a total of 22 plus basically 3 plus 3. I'm not verifying those numbers, I'm just telling you what I'm seeing out there. So both of these new studies are really exciting because this is something new about nuclear thermal rocket, both coming from the Defense Department as well as NASA. In addition, now this I'm going back to some studies from years ago. Mars habitats, unlike what we had with Apollo, if we're going to go through the time and effort and money and sending them there, we're probably going to have astronauts on board for periods of weeks, probably months, likely months, where the habitats are here. You see 2 stories tall. They land on their own. They probably have wheels so they can be moved in place and connected by tunnels, and laboratories to allow in situ study of resources there on Mars. And there it will make it worth your while to send people there to study the Mars habitat for protracted periods of time. In fact, the conjunction missions have them on Mars for well over a year, where you can set up power stations, probably nuclear powered stations, because you need more than just solar cells there, and prolonged study of the environment, search for life, and be able to use and test out the resources for propellant and human consumption. And actually study for past life forms, probably not as daring as this artist who thought that astronauts might be able to be even braver than they actually are here, propelling down the side of a canyon. Concluding thoughts, if I leave you with anything here, is that there's three main problems. There's a propulsion problem that we know how to solve. I should have mentioned, by the way, back in the 50s and 60s, we built and test fired 20 nuclear thermal rockets here on the Earth. We didn't flight test them, but we test them here on the Earth. One of them up to 1 hour of burn time. So we know nuclear thermal rockets work. We've built them, we've tested them. All we have to do is spend money to build the flight articles. The other two problems are less mature. Artificial gravity for crew module design, that's a science problem that we really don't know how much artificial gravity we need. And the ambient radiation protection, we know how to solve the problem. It's just that the solutions are not very good. We need a better idea. These are the three main problems. One's a science problem, one's an engineering problem, and one is basically a funding problem. But those are the three problems that we have to solve in order to send people to Mars. So we are a long, long way from seeing Matt Damon walk around as the Martian in that recent movie. Although I'm not a space biologist, this is just one person's opinion. This last chart, I'm not speaking for the agency, but I still wonder sometimes, this might not be, there may be intelligent beings elsewhere where you see these two Martians holding up a picture and one guy's saying, hold it still, Larry, it's taking another picture, hiding the Martian cities in the background. It might be the case, who knows? And I will leave with that. Thank you very much. If there's any questions about sending people to Mars or the Glenn Research Center, I will take them right now.
All right. Take a look at the chat here. We do have one question. Is the European Space Agency working with us, or are they developing their own mission? And how about the Chinese?
It's a little bit outside of my purview here. Robotic missions, I believe the Chinese are doing their own thing. I think we are always collaborating with the Europeans. I know they have their own separate program for the robotic. My guess is that we're probably always working with them on that. As far as actually sending people to Mars, my understanding is that we're sort of on our own. I don't know if the Europeans are doing very much on that. I'm confident that what I read in the newspapers, again, I have no inside information. What I read in the newspapers is that the Chinese probably are doing their own internal studies. So it probably breaks along those lines, give or take.
Okay. Hey, Janice, thanks you for a great program. I don't see any other questions in here just yet. If anyone else has questions, you can put them in chat, or you can unmute yourself if you'd like to just ask. That's fine as well. I have another question. Is, would the moon be used as a base of launch or other purpose?
There is discussion of doing that. Again, I can't comment on official policy. Let me just, trajectory design is part of my background. Let me just point out some of the challenges of something like that. If you launch from the moon, okay, there's one advantage and there's other disadvantages. There's an old, it's sort of a joke, but it's actually true, that if you go into if you launch to low Earth orbit, you're halfway to any place in the solar system. And from a delta V, an energy point of view, that's actually pretty close to being correct. It's not distance that matters, it's energy, total energy, kinetic plus potential. So once you get into low Earth orbit, you're halfway to anywhere. If you go to the moon, you're actually putting yourself into gravity well of the moon, so you have to mitigate that. But you're actually further out into the gravity well, so you get a slight advantage. The disadvantage of that, though, is that you have to match your outgoing target vector, which is declination, right ascension, total energy, and it complicates the planning tremendously. If you're launching from the moon or even in orbit from the moon, it complicates things immensely, especially when it comes to launch windows. So it's not always clear that doing a launch base, and then you have to duplicate basically what's at our launch facility, Cape Canaveral, Kennedy Space Center, or any place else, on another body. And that is someone who's planning that has to factor all that in. You have to factor all the ground operations, the launch pad, the propellant facilities, all of that. And you have to ask yourself, is it worth it just to save myself some delta V and reduplicating all that and the complications of launch windows, by moving my basically Cape Canaveral to the moon? I'm not so sure that's a good trade.
We've got another question. Someone's asking, what can avid astronomers who are not professionals do to advocate for increased funding or awareness for the space program?
Okay, this one's easy for me. I cannot advocate for additional funding, nor can I ask you to do that. So I have to graciously decline to answer that question. All I can do, and it's as a government employee, as a civil servant, is share with you information that you, the taxpayer, have paid for. I cannot ask you to advocate something that will benefit me or my colleagues directly. So I'm sorry, but I have to duck the question.
Okay. I'm not seeing any other questions at the moment here. If anybody else has anything, just let us know.
I will say this, I should have done my homework. Don't you have is it your county that has a giant open field that has no light pollution that you can go out and look at the stars at night? Or am I getting my counties mixed up?
In Geauga County, we do have a fair amount of open fields. We also have the observatory in Montville, part of the Geauga Park District, and the name of it is escaping me right now.
Is it a giant open field that it gets very, you can just use that to set up your telescopes and look at night because you don't have a lot of extraneous light sources?
There are a lot of places around here where you can do that, and the one particular is called Observatory Park, is in Montville, but then there is just generally a lot of farmland in this area. Yes,
it's a silver tier dark sky.
Okay. The reason.
Oh, what was that?
It's a silver tier dark sky park. It's one of about 40 in this country. It's the only one.
Okay, is it
Ohio?
It's the only one in northeastern Ohio?
Yes, it's the only one in the state of Ohio, actually. The only dark sky, designated dark sky park.
Okay, then I think that's it. Several years ago, with the 50th anniversary of the Centaur Upper Stage, which is, by the way, part of this whole story that we never really got to, we did several commemorations of the Centaur Upper Stage, which is the vehicle that the Glenn Research Center actually made a successful vehicle and launched many of the interplanetary missions that this country ever launched. Well, one of the many things I was trying to get going was an observatory night to see that. And amazingly, that first successful Centaur Upper Stage is still in orbit. Normally these things go into interplanetary orbit and we never to be seen again, or they burn up. But that one, AC2, the first successful one, is still in orbit. And we actually got ephemeris data where we could see it from your dark sky field out there. And we went out there one time, and unfortunately the weather was not cooperating, but our latitude was such that you actually could see the Centaur Upper Stage. So That was something we tried to pursue, and we never were successful, but it's kind of a cool concept if you think about it.
Okay, let's see. We do have one more question that I see. Someone wants to know what students all over the world can do for the Mars project.
Well, I know we have
Especially
internship.
engineering students, I think. Yeah, there's a second part to it, a few down.
Okay, I would encourage them to check into, and I don't have the website, but I'm sure it's tied onto our NASA.gov website. We have student internships at all the NASA centers. They're fairly competitive, but I would encourage you to check those out, and they offer opportunities for students to come and work with us for short periods of time to learn something about. And it's not just Mars missions, it's aeronautics, it's science, it's material science, power systems, propulsion systems, it's all sorts of things. Okay, listen, we could call it a wrap. I appreciate the time, and stay tuned. We're hopeful that sooner or later we'll be talking about sending people to Mars, and it will be an exciting time.
All right. Well, thank you very much. That was a very informative and entertaining presentation. I very much enjoyed it. So, and thank you everyone for joining us this evening. And we'll see you hopefully at next month's Skywatchers program.
Okay. Bye-bye.
Thank you. Goodbye.
Oh, and I see some pictures there. Okay. All right. Can you still hear me?
Yes.